Welcome everyone. In this video, I want us to talk about modulus argument, and specifically, I would like us to learn how to write a complex number in polar form. So let's get into it. So to do so, let's consider a complex number. Let's say z equals x plus I, and let's represent complex number in an Argand diagram. So we have our pair of Cartesian plane of x and y axis. So this is the x-axis and that is the y-axis. So it's going to look something like this. And this is P. The coordinates, the Cartesian coordinate of P are x, y. And then the angle between the x and the line, the x-axis and the line is, let's call it theta. So this is x, this is y, and that is r. So our Cartesian coordinates are x, y, and here we say our polar coordinate. Our polar coordinate should be r, theta. Now, how can I represent this complex number in polar form? Let's represent this complex number in polar form. So from the diagram, we see that sine of the angle theta, sine is supposed to be opposite over hypotenuse. The opposite side is y and the hypotenuse is r. So from this, we see that y is just r sine of theta. Similarly, the cosine of the angle theta is adjacent over hypotenuse, and the adjacent side is x divided by hypotenuse, which is r. So it implies x is equal to r cos theta. Now, for the complex number x plus iy, this is equal to r cos theta plus r I sine theta. So if we factor out r, x plus iy should be equal to r into cos theta plus I sine theta. There you go. So this is how we write a complex number in its polar form. Let's take some examples. Example: express in the form r into cos theta plus I sine theta the following complex numbers. Number 1, 1 minus I root 3. Number 2, 2. Number 3, negative 5i. And number 4, we have negative 2 plus 2i. So let us express each of the following complex numbers in polar form. So let's begin. Solution. Now, we know that the polar form is r into cos of theta plus I sine of theta, where r is the modulus and theta is the principal argument. So in simple terms, we can express in polar form by finding the modulus and the argument. So let's begin with number 1. Number 1, we have 1 minus I root 3. Remember, the modulus r should be square root of 1 squared plus root 3 squared. So r is equal to 1 squared is 1, root 3 squared is 3. 1 plus 3 is equal to 4. So r is equal to square root of 4. Sorry. R is equal to square root of 4. Hence, the modulus is equal to 2. That is the modulus. Next, we also have to find the argument. And to find the argument, it is always very important to represent a complex number on an Argand diagram. That is, so let's draw a pair of x and y axes. So when we draw this, the complex number, the real part of the complex number is positive 1. So that is in the positive x-axis. The imaginary part is negative root 3. So this should be in the 4th quadrant. So this should belong to this quadrant right here. So our rotation has to be clockwise. Hence, I know that the argument has to be negative. So this should be square root of 3, which is negative, and this should be 1. So, and then this is our angle theta, which is supposed to be negative. So, tan of root 3 over 1. So, the angle theta is supposed to be tan inverse of square root of 3. We know that tan of 60 square root of 3, tan inverse of, so the angle theta here should be 60 degrees or pi over 3. So since this is clockwise, so the argument has to be negative. So this should be negative pi over 3. Now that we've got the modulus and we've got the argument, now we can represent the complex number 1 minus I root 3 in polar form as, so the modulus is 2, so this is 2 into cos of negative pi over 3 plus I sine of negative pi over 3. So that is the polar form of the complex number 1 minus I root 3. Now let's look at the second one. The second problem is question number 2. We have 2. Now we know that the complex number is of the form a plus bi. So since this is equal to 2, it means that the imaginary part is equal to 0. Now we want to express this in polar form as r in bracket cos of the argument theta plus I sine of the argument theta. So since the imaginary part is 0, the modulus, which is supposed to be the square root of a squared plus b squared, is going to be r is equal to square root of 2 squared plus 0 squared. 2 squared is 4, 0 squared is 0, so the modulus r is square root of 4. And square root of 4 is equal to 2, the modulus is equal to 2. Now, next we have to find the argument. How do we find the argument? Again, to be able to do that easily, let's represent this on our Argand diagram. So we have the y-axis and the x-axis. So let's suppose this point right here is 2. And then, since this is of the form 2 plus 0i, it means the imaginary part is 0. So we have a line right here on our x-axis. So it means that the angle between our vector and the x-axis is 0. So our argument here basically is equal to 0. So we can write this in polar form. So 2 is just equal to 2 into cos of 0 plus I sine of 0. So that is the polar form. That is the polar form. Now let's look at the third one. The third problem, negative 5I. Now let us represent this complex number, which is basically an imaginary number in polar form. Now we know that any complex number is of the form a plus bi. So you can see here that the real part is 0. So we could also rewrite this for convenience sake as 0 minus 5i. Now let's start by finding the modulus r. So r is equal to the square root of 0 squared plus negative 5 squared. 0 squared is 0, negative 5 squared is 25. So r is square root of 25. So r is equal to 5. Now that we've got the value of r, let us find the argument. Now to find the argument, let us draw our diagram right here and here. So since the real part is 0 and the imaginary part is negative 5i, so it has to be on our imaginary axis. Let's assume the point is right here. So our rotation, this should be clockwise right here. So here I do not necessarily need any calculation, because here I can see that the angle between this point and this point is just pi over 2, or 90 degrees. Since we are going clockwise, the argument should be theta equals negative pi over 2. So equals negative pi over 2. So now we can represent this in polar form. So negative 5i is equal to 5 into cos of negative pi over 2 plus I sine of negative pi over 2. So that is the polar form. And the last question. The complex number is negative 2 plus 2i. So let's start by finding r. R is equal to square root of negative 2 squared plus 2 squared. R is equal to square root of 4 plus 4. 4 plus 4 is 8, so this is square root of 8. And 8 is the same as 4 multiplied by 2, which can be written as square root of 4 times square root of 2. Square root of 4 is 2, so r is equal to 2 square root of 2. And similarly, we can, let's find the argument. So remember, it's always important to represent this on the diagram so we can actually locate the correct quadrant. So in the complex number, the real part is negative and the imaginary part is positive. So this is negative x and positive y. So this must be in quadrant number 2, where this is 2 and this is negative 2, or I can just write 2. And here you see that the angle theta, or the argument, must be obtuse, since it is in the second quadrant. So tan of the angle theta, or let's call this associated angle right here, let's call it alpha. So tan of alpha should be 2 divided by 2. So tan of alpha is equal to 1. So we know that tan of 45 degrees is 1. So alpha, tan inverse of 1 must be 45 degrees. Or we can say it is pi over 4. Now this is this associated angle right here, pi over 4. We know that this angle plus this angle must be pi. That is pi over 4 plus theta must be equal to pi, which is 180 degrees. So the angle theta must be pi minus pi over 4. So this is the same as, this is pi over 1, so multiplying by 4. So this is 4 pi over 4 minus pi over 4, and which becomes 4 pi minus pi all divided by 4. 4 pi minus pi is 3 pi over 4. So this is equal to 3 pi over 4. So that is the argument. Now we can write the complex number in polar form, as that is negative 2 plus 2i is equal to the modulus we got 2 root 2. So here we have 2 square root of 2 into cos of 3 pi over 4 plus I sine of 3 pi over 4. There, that is the polar form.